Deep within the crushing hearts of neutron stars, some of the densest objects in the universe, physicists theorize the existence of a truly bizarre substance. It's a material so extreme, so alien, that it pushes the very boundaries of our understanding of physics. This isn't just another exotic particle or a newly discovered element from a distant galaxy. This is something far more fundamental, a state of matter known as strange matter. Strange matter is a hypothetical form of quark matter, and if it exists, it could very well be the most stable, and consequently, the most dangerous substance in the entire cosmos. Its existence stems from a fascinating area of particle physics involving the building blocks of protons and neutrons, quarks. We are all familiar with the atoms that make up our world, our bodies, and everything we can see and touch. These atoms have a nucleus at their core, which is composed of protons and neutrons. For a long time, we thought these were the fundamental particles. But we now know that protons and neutrons are themselves made of even smaller particles called quarks. Specifically, they are made from two types of quarks, up quarks and down quarks. A proton is made of two up quarks and one down quark, while a neutron consists of one up quark and two down quarks. These up and down quarks are the lightest and most stable types. However, particle accelerators have revealed that there are four other flavors of quarks: charm, strange, top, and bottom. These other quarks are much heavier and are highly unstable. When created in high-energy collisions, they decay into the more stable up and down quarks in a fraction of a second. This is the normal state of affairs as we observe it on Earth and in most of the universe. But what if there was a way for these other quarks to exist in a stable form? This is where the idea of strange matter begins. The theory, known as the Bodmer-Witten hypothesis, proposes that under conditions of extreme pressure, something extraordinary can happen. So extreme, in fact, that it can only be found in the core of a neutron star. Inside a neutron star, the gravitational forces are so immense that they crush atoms completely, squeezing electrons and protons together to form a sea of neutrons packed tighter than an atomic nucleus. The pressure is unimaginable, billions of times greater than anything found on Earth. Under this colossal pressure, the neutrons themselves are crushed, and the up and down quarks that compose them are set free, forming a dense soup of quark matter. The hypothesis suggests that in this environment, it becomes energetically favorable for some of the up and down quarks to transform into strange quarks. This transformation creates a new substance, a mixture of up, down, and strange quarks in roughly equal proportions. This concoction is what we call strange matter. And here is where things take a truly terrifying turn. The theory doesn't just stop at its creation, it suggests that strange matter might be the true ground state of all matter. In physics, a ground state refers to the lowest possible energy level of a system. Systems naturally want to settle into their ground state, just as a ball will always roll to the bottom of a hill. If strange matter is indeed the ground state, it means that the normal matter we are all made of, with its protons and neutrons built only from up and down quarks, is actually in a higher energy, less stable state. It's what physicists call a metastable state. Think of it like a diamond and graphite. Both are made of carbon atoms, but diamond is in a metastable state. Given enough time and the right conditions, a diamond would eventually transform into the more stable graphite. Our matter might be like that diamond, seemingly stable, but only because it hasn't been given the right push to fall into its true ground state. That push could come from a single, tiny piece of strange matter. The hypothesis continues that if a piece of strange matter, even one as small as an atom, were to come into contact with a nucleus of normal matter, it would trigger a catastrophic chain reaction. The strange matter would act as a template, immediately converting the protons and neutrons of the normal nucleus it touched. The quarks within that nucleus would rearrange themselves, with some converting into strange quarks to reach that lower, more stable energy state. This newly converted nucleus would now itself be a piece of strange matter. It would then touch its neighboring nucleus, converting it, which would then convert its neighbor, and so on. The process would be like a cosmic contagion, spreading outwards at nearly the speed of light. A single speck of this substance, called a strangelet, could theoretically convert the entire planet Earth into a dense, lifeless sphere of strange matter in a matter of moments. There would be no explosion in the traditional sense, no fiery blast. It would be a silent, instantaneous transformation. The planet would simply become something else. An inert, superdense ball of strange matter, roughly the size of a large stadium, orbiting the sun. All life, all history, all complexity, would be gone, replaced by this bizarre, uniform substance. This horrifying scenario is often compared to the fictional Ice Nine from Kurt Vonnegut's novel Cat's Cradle. In the book, Ice Nine is a special form of water that is solid at room temperature. If a crystal of Ice Nine touches liquid water, it instantly freezes all of it into more Ice Nine. Strange matter is the real-world scientific equivalent of this concept, but on a cosmic scale with far more permanent consequences. It's the ultimate Grey Goo scenario, a phase transition that consumes everything in its path. So, where might we encounter this cosmic doomsday substance? The most likely source would be from the cosmos itself. Neutron stars are the primary candidates for housing strange matter cores. If two neutron stars collide, an event we have now observed with gravitational wave detectors, it's possible that droplets of strange matter, these strangelets, could be ejected into interstellar space. These cosmic bullets would then travel through the galaxy for millions or billions of years. Most would likely just drift through the vast emptiness of space. But if one of them were on a collision course with a star or a planet, like Earth, the consequences would be absolute. The arrival of the strangelet would be the end. Another possibility, though highly debated, involves particle accelerators here on Earth. Some have expressed concern that high-energy collisions, like those at the Large Hadron Collider, could accidentally create a stable strangelet. The idea is that smashing particles together with enough force might replicate the conditions inside a neutron star for a fleeting moment. However, the scientific consensus is that this is extremely unlikely, bordering on impossible. Firstly, the energies achieved in our accelerators are many orders of magnitude lower than those in cosmic ray collisions, which have been bombarding Earth and other celestial bodies for billions of years. Cosmic rays, which are high-energy particles from space, hit our atmosphere with far greater force than anything we can generate. If such collisions were capable of creating stable strangelets, it would have already happened somewhere in the solar system. The fact that the Moon, which has no protective atmosphere, is still made of normal matter after billions of years of cosmic ray bombardment is strong evidence against this possibility. Furthermore, even if a strangelet were created, theory suggests that very small strangelets would be unstable and would evaporate almost instantly. It's believed that a strangelet would need to be of a certain minimum size to be stable, a size we are nowhere near capable of producing. So, while the doomsday scenario of a human-made strangelet is a popular trope in science fiction, the reality is that the threat, if it exists at all, is an astronomical one. It's a risk that comes from the sky, not from a lab. The very existence of strange matter remains a hypothesis. We have not yet been able to directly observe the core of a neutron star to confirm its presence. Scientists are looking for telltale signs, such as how neutron stars cool over time or their precise mass-to-radius ratio, which could give us clues about what's happening deep inside. If strange matter is real, and if it truly is the ground state of matter, it raises profound philosophical questions. It would mean that our entire visible universe, with all its beautiful complexity, from galaxies and stars to planets and life, is fundamentally unstable. It suggests that we exist in a delicate, temporary state, always at risk of being corrected back to a simpler, more basic form of existence. The cosmos would be like a supersaturated solution, waiting for a single seed crystal to begin a universe-wide transformation. This idea places our existence on a precarious edge, highlighting the fine-tuning of the physical laws that allow us to be here. It's a humbling and slightly unnerving thought that the matter we're made of might not be the final, most stable configuration. But for now, strange matter remains in the realm of theoretical physics, a fascinating and mind-bending concept that pushes the limits of our imagination. It serves as a powerful reminder that the universe is filled with mysteries far stranger than we can possibly conceive. The study of such extreme possibilities is what drives science forward. It forces us to question our most basic assumptions about the nature of reality and to look for evidence in the most extreme corners of the cosmos. Thank you for joining us on this journey into the heart of matter. If you find these cosmic mysteries as fascinating as we do, be sure to subscribe to Space Repo for more deep dives into the wonders and terrors of our universe.